as the distance in the distance conjecture in the context of swampland program. Distance conjecture says that if you start from a point P in the moduli space and move towards another point Q, which is at infinite distance, you will be getting a tower of states which become exponentially large, become exponentially light with this geodesic distance. It also has an ADS version, which states that as you send in ADS curvature to 0, you will be getting a tower of light states, and the masses go like lambda to the alpha, where alpha is an order 1 constant. Now, the thing is that people normally use the metric in the kinetic term to define the distance. Here, what we aim to do is to also take into account effects of the scalar potential. And when we want to take into account these effects, naturally energy enters into the game. And to see this intuitively, take this spiral potential. If you want to probe this potential and your probe has a low energy, it will go along the spiral towards the point in the minimum. But if it has enough energy to pass the local barriers, it will go straight towards the minimum in the middle. So the distance that it actually measures depends on the energy that it has. So with this in mind, we propose a Euclidean action of the solution that it interpolates between different vacua, normalized by energy density as the distance. And in doing so, we are actually inspired by the cobordism conjecture. So what I will do in the rest of the talk is that first, for the case that there is no scalar potential, I will show that this proposal leads to the usual delta phi that we know. And then I will add effects of the scalar potential as long as gravitational back reaction does not matter. And finally, I will also include the effects of gravitational back reaction. So let's start with a fixed background. When the scalar, and first when the scalar potential is 0, and you have a scalar field, which is a function of only one spatial direction that we call tau, we can work out the solutions and read the tension, which goes like delta phi squared over delta tau. Notice that as delta tau goes to infinity, this tension vanishes. However, our proposed distance, which is the normalized tension, is finite and gives you delta phi, and it can trivially be generalized to the case with multiple scalars. Now, when we add the scalar potential and solve the equations of motion for energy rho e, which is a constant of motion in this case because the system is time independent, and find the tension, we end up with this expression for the tension. This is actually in the case that rho e is equal to minus v. This is nothing but the tension of the Coleman-de-Lucia bubble, and is the Coleman-de-Lucia solution. But this solution is in general more general than the Coleman-de-Lucia solution, which enables us to find the solution and compute the distance in the cases when we don't have a solution for a tunneling solution or a Coleman-de-Lucia solution. Now we normalize it to get the distance, and this can be trivially generalized to multiple scalars. Now, this proposed distance matches some interesting object. In order to see what this interesting object is, I will briefly talk about a Mappertui action and Jacobi metric. So there is another formulation of classical mechanics in terms of Mappertui action, which is actually integral over twice kinetic energy. This action gives you trajectories of constant energy, and you can rewrite it in the form of a line element and extract a metric from it. So actually, solutions to equations of motion will be geodesics of this metric, which we call Jacobi, which is called Jacobi metric. And this exactly matches our proposed distance in this case. So the proposed distance will be Jacobi line element normalized by a constant, which is the energy density. So it's a metric in the traditional sense. It has nice properties. It is positive definite. It is symmetric. It satisfies triangular inequality exactly because it is the action evaluated on the path that minimizes it. And it gives you back the moduli space distance when the potential vanishes. So it kind of interpolates between the Coleman-Deluccia tension and moduli space distance. Now let's do an example. Let's model a conical topological transition by this simple potential and say that we want to compute distance between a point on r-axis and a point on rho-axis. We can do the equations of motion and find the trajectories, which I have plotted here. The blue ones are the low energy ones, the red ones are the high energy ones. As it is obvious, the low energy solutions are actually governed by controlled by the scalar potential. They're similar to equipotential lines. And the high energy ones are actually similar to the motion of a free particle, as if there's no potential. We can compute the distance as we expect. When rho goes to infinity, it gives you the moduli space distance. And when rho goes to 0, it takes this form, which becomes very large if r and rho are non-zero, which is a reflection of the fact that you won't have enough energy to actually climb the potential. Okay, now let's include gravitational effects. We take a flat metric, an F4W metric, as an ansatz and solve the equations of motion. The first thing that we notice is that energy is no longer constant because the system is time dependent, and energy varies with phi according to this equation. We can always set the initial conditions such that the solution exists. We can also generalize to the case with multiple scalars. Sorry for the noises, by the way. And now we want to propose a generalization of our distance for this gravitational case. What we did was that we sliced the solution into slices with a small delta phi, so that in each slice, lambda is a constant, and we integrated over the flat distance in each of these slices. And we ended up with this proposal for the distance. It has nice properties. The first one is that in gravitational decoupling limit, it recovers Jacobi metric. It is positive definite. As we expect, when v is 0, it gives you the moduli space distance. It is also symmetric if we adjust the initial conditions, so that if we start with lambda 1 from here, go to lambda 2, then again go back with lambda 2 to the point 1, it will be symmetric. However, triangular inequality is not guaranteed. And in some special supersymmetric cases, which I mention later, we'll have triangular equality. So one nice feature that this distance has is that it will recover the ADS distance conjecture for supersymmetric cases. If we apply the equations of motion to our proposed distance, we get this logarithmic form. And for the supersymmetric cases, that the beginning and end points are fixed points, this exactly gives you back logarithm of Vf over Vi, which is the distance in ADS distance conjecture. Moreover, if we assume that mass goes like lambda to the 1/2, which holds for all non-scale separated supersymmetric ADS vacua, we recover this exponent, this coefficient in the exponent. as if one extra dimension is decompactifying as the radius of ADS is increasing. Okay, now let's do an example, which is the supersymmetric vacua. Take four-dimensional n equals 1 supergravity. It has a scalar potential which goes like this, a positive term from supersymmetry breaking and a negative term from the superpotential. And let's say that we want to find the solution and compute distance between two ADS vacua, which are supersymmetric. And in the middle, and we can have supersymmetry breaking and de Sitter vacua and so on. There exists a BPS solution interpolating between the supersymmetric vacua, which is given by these first-order equations. In this case, we see that the nonlinear equations are reduced to first-order equations because of supersymmetry. And then we can see that the kinetic energy is equal to supersymmetry breaking. So in the initial and final ADS vacua that are supersymmetric, you have no kinetic energy, and these are actually fixed points. So we recover ADS distance conjecture, and we'll have triangular equality for the distance. Also, in the case where the difference between these two potentials is smaller than the potential itself, you can expand the exponential in terms of the BPS domain wall tension, and what we get is a normalized BPS domain wall tension. All right, so I will end with some discussion and future directions. As I said earlier, in the gravitational case, we don't have triangular inequality. It's not guaranteed because our distance is not a metric in the traditional sense. We try to do some friendship between this distance and metric in the gravitational case. Actually, the analog of Jacobi metric can be computed using some tricks in the gravitational case for the time-dependent system. However, the problem is that the contribution from a gravity sector and scalar field sector annihilate each other, and you will get 0 for 0 scalar potential. So this metric will not be a good measure of distance. Also, we try to do some spherically symmetric ansatz. And also in that case, we ended up with horizons. So yeah, that's it. As for future directions, because all this formalism can be rewritten in the Hamiltonian language, and there, for different purposes, people have extensively studied the symmetries and where solutions exist and how they behave and so on. So probably if someone is familiar with those tools, could make progress in doing this friendship between metric and distance in the gravitational case. And also, it would be good to incorporate fluxes because now we have only a scalar field. This also, I expect it can be done more easily in doing the Hamiltonian in the Hamiltonian formalism because you can add the gauge fields as a part of the momentum. Yeah, that's it. Thank you for your attention.
Thank you, Amineh, for the very nice talk. Are there any questions from the audience?
Yes, Nacho, please go ahead.
Hi, Amineh. Thanks for the great talk. One quick question. So on the you so far have considered just like some fixed potential, but if you had like imagine like some matter that would also like depend on the fields, could that do you think that would also affect the notion of distance, as it would also, for example, affect the equations of motion, like for example some brane like with some back reaction that on the moduli?
Yeah, probably when you can The scalar fields associated to the brain can be part of this multiple scalar thing. And the potential part can be incorporated in the potential. So the formalism will work in that case.
Even if it's like, as you said, if it's not like spherical, symmetric and anything, you think that it could be like extended?
I mean, any form of energy will back react on the FRW metric and give it a curvature. So yeah, I think it will work.
Okay, thanks.
Jesus?
Yeah. Thank you, Amineh, for the nice talk. I have a question about this definition of distance. You say that it is not symmetric, but if you change the initial condition, you can make it symmetric. Can you further explain on this point?
Yeah, let's see. Let me see where
Yeah,
you
this
go.
slide.
Okay. Yeah.
Mhm.
And what I mean is that if you start from this point phi with
Yes.
say energy lambda 1, and you flow to the point phi f,
Mhm.
you get another energy because it evolves. You get another energy lambda 2.
Mhm.
Now, if you want to go from point 2 to point 1, you have to start with lambda 2, not lambda 1.
Mhm. But
So you go from phi 1 with lambda 1 to phi 2. And if with lambda 2, if you reverse this with lambda 2, you will again go to phi 1 with lambda 1. You cannot start from point 2 with the same energy that you started at point 1.
okay. So you need to change the initial energy to go from point 2 to
Yeah.
point 1.
Yeah.
Okay.
Yeah.
Thank you.
Are there any other questions from the audience? If not, let's thank Amineh again. And now, Amineh, would